Oxymercuration Demercuration. Oxymercuration Demercuration is a two-step process that adds water across an alkene. This is an example of a Markovnikov addition. Of water, or HOH. Since it's a Markovnikov addition, the H goes on the less substituted side of the alkene, and the OH goes on the more substituted side. Now, we've had Markovnikov additions before, such as with acid and water. What makes oxymercuration demercuration important is that it does not go through a carbocation. Meaning the chances of rearrangement are severely diminished, such as if we were to add acid and water to this alkene, the major product that we would get is this tertiary alcohol. Because upon protonating the alkene, we form a secondary carbocation. That secondary carbocation can rearrange to form this tertiary carbocation, and this tertiary carbocation is what water attacks. Deprotonation of the water afterwards gives you the product here. Oxymercuration demercuration does not involve a carbocation. As a result, when we treat it first with mercury acetate and water, followed by sodium borohydride, we get the product where a rearrangement did not occur. Okay, mechanism of this reaction. Start off by adding mercury across that pi bond. I'm going to draw out the acetate groups, though it's not necessary. This mercury has a lone pair. The electrons go to one carbon. The electrons from the pi bond go back up to the mercury, and then one of the acetate groups is kicked off. It could be either acetate groups. Moreover, this mercury can come from the top face or the bottom face, resulting in a racemic mixture of the two. This mercury is on one enantiomer, the mercuries are both wedges. On the other enantiomer, they're both dashes. Water then attacks and opens up this three-membered ring. This step is actually an SN2 step. Water comes from behind the carbon-mercury bond and breaks the carbon-mercury bond. So essentially at the carbon where the water attacks, that's the one that is inverted, like so. As a result, the mercury and the OH have a trans relationship to each other. If this mercury was a dash, then the OH would be a wedge. Quick proton transfer. This is as far as the mechanism as you need to know for this process. If we dissect it step by step, we have the lone pairs going to this carbon, the electrons from the pi bond go from the other carbon up to the mercury. You could have drawn it in another manner. Where the mercury electrons go to the other carbon, and these electrons go up to there. And you could even kick off the other acetate group. It does not matter which acetate group you kick off, nor does it matter the exact direction of the arrows, except you have one going from the mercury to the carbon, and then the bond sways away from the other carbon to the mercury. And that gives you the mercuronium salt. You could have drawn it as the mercury is both wedges, or you could have drawn it as both dashes. Does not matter, as these two are enantiomers. So by writing racemic underneath this, you cover both your bases. Now, water attacks on the more substituted side. This is odd for a couple of reasons. One, it's an SN2 reaction with water, which is not a typical SN2 nucleophile. Better get rid of. So it's not typically used as an SN2 nucleophile. Moreover, the nucleophile is attacking the more substituted side. These two things tend to go against standard SN2 reactions. The reason it's allowed in this case is this three-membered ring with a mercury group. It's not your typical SN2 electrophile. In fact, as it's drawn, the two bonds look equal, but really, in actuality, they are not. This is such a good leaving group, it's leaving just slightly before the nucleophile attacks. Another way of thinking about it is one of these bonds to the mercury is actually longer than the other one. The bond that's longer to the mercury is the one whose carbon is best equipped to handle a positive charge, because this mercury is already starting to leave, and as it already starts to leave, you're starting to develop this delta positive charge here. And that is what attracts even the weak nucleophile of water. Yes. Okay. So that's the reason for the stereochemistry and also the regiochemistry, where the water attacks. Now, the second step of the oxymercuration demercuration step, the sodium borohydride replacement step. That mechanism is actually quite complex. And it goes over intermediates referred to as radicals. Radicals we'll cover later on, and so you are not responsible for the mechanism for the replacement of the mercury with the hydrogen. What you should know, though, is that there's no control over where that hydrogen ends up on that carbon in terms of wedge or dash. In this example, it doesn't matter because both of these are hydrogens. However, if instead of using sodium borohydride, use NaBD4, so replacing the mercury with deuterium instead of hydrogen, you actually end up with 4 products. Here's 2 of them. So you get a racemic mixture here, because this here is racemic. And the other 2 is where you have the deuterium is replacing the mercury, and you end up with the same stereochemistry. 4 products total.